All right, well, welcome back. So in the previous lesson, we had a look at some applications of integration. Namely, we had a look at two concepts being the work, and we also had a look at the average value function. So those are the two concepts that we have looked at in the last lesson. They weren't as challenging um, as what we might be seeing today. All right. So today's lesson will actually be focusing on two more concepts, one being the arc length of a function, and we'll also be having a look at the surface area of a function. All right, so we can so we have bound areas and volumes by using Riemann sums. So it is also natural to assume that we can do the same for to determine the length of a curve in a given interval. So for example, let's say we have a function f of x that is continuous. So make sure that the function is continuous on the interval ab. So if we draw this, let me draw a better curve. Okay, so that's our curve here. So let's say that this point here is going to be our a. So this is our axis. This is a. And this point here is, let's say it's b here. So what we're gonna do, I'll actually move this to the left a little. All right, is we're gonna try to break up the length into n sub-intervals once again. So we have the points. We can approximate the curve, the length of the curve by dividing the interval into n sub-intervals. So let's say we divide this point here. We divide here, 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 and it just keeps on going. And so each of them, the distance between these two will have a length of delta x. So same thing as before. And we have the points located at, so this is P0. This is, the starting point is P0. This point is P1, P2, P3, and so on. Until you reach Pn, let's say. And these are located at the point x 0. So let's call A be x0. This be x1, x2, x3, and so on. All right. So that's how we're gonna be approximating the length here. So let's say we have another curve, for example, say this is gonna be our curve. And we try to connect the points here. So if we say this is P0, being x0, fx0, and let's say we have another line, another point here being P1, x1, fx1, and say we have another line, point here being P2, x2, fx2. And suppose that this just keeps on going on forever. Then we could connect the lines here. See that, well, if we connect these, we could actually approximate the length here. If we consider more lengths between, more points between the curve. So for example, so I'm gonna take away these points. I'm gonna add a bit more points here. So say I add this point, this point, this point, this point, maybe one here, and one there. So I could actually approximate more of these points. So if we have more points, we could actually obtain what the arc length of the curve is. So that's what we're trying to get at here. And it will just keep on going. Okay, so if we draw straight lines that can connect the endpoints in each subinterval, the total length of the curve is approximately the sum of the lengths of the straight line. So if we have infinitely many points, it will actually be equal to the curve, the length of the curve. Okay, So once again, the length of the line segment in the ith subinterval can be given as the distance between pk minus 1 and pk's. So this length here is the length of the segment. Line segment. And so we could actually determine the total length by using Riemann sums as n approaches infinity. So if we have L as the length of the curve, this could be written as the limit as n approaches infinity of n, or from the sum from I is equal to 1 to n of pi and pi minus 1, this length here. So it's the length between each of the points here. So the length of any straight lines can be determined using the formula for the distance between 2 points. So remember that the distance formula, pi minus 1, pi, is actually given by the square root of the final x coordinate, which is going to be xi, and then the final y coordinate, xi minus, or the initial coordinate, I minus 1 squared. And then you're going to add the y coordinate, which then will actually be our function coordinates. So the final position for the function is going to be when we have fxi. The initial function's position is going to be fxi minus 1. And the whole thing is squared. Then we take this, all of that squared. So if you want, this is also the same as saying, well, x2 minus x1 squared plus y2 minus y1 squared. So that's what the length here is using this formula here. And so if we call this part here, let's say that's going to be our delta x, and this part here is going to be our delta y, then we could actually just rewrite this as the square root of delta x squared plus delta yi squared. And this one we will actually be using later on. So now by using the mean value theorem, we know that there is such a point in each subinterval, let's say delta I star, such that, well, fxi minus fxi minus 1 is equal to the derivative of f of xi star multiplied by xi minus xi minus 1. So the mean value theorem actually plays an important role, which is something that we have learned or talked about in the first lesson. So let's see, where is this here? So this is the mean value theorem once again. So we say that if f is a function that is continuous on the closed interval ab, differentiable on the open interval ab, then there's a number c such that f prime c is equal to the slope of the secant here. Well, this is very easy to just rearrange because what we have here is that, well, if we just bring this to the other side, we would just get, well, fb minus fa is equal to the derivative at c of b minus a. So that's the technique we're using at this point here. All right, so let's go back. Okay, so because of this, we could then write delta y on the left-hand side from this. So we have delta y I. This can then be written as f prime of xi star times delta x. So note that here, delta yi, if we put f prime of xi star times delta x back into the length formula. So what we're going to do is take this and put it back into here. That's what we're going to do next. So then we would just get the length pi minus 1 pi. This is equal to just the delta x squared plus the derivative of fxi star times delta x whole thing squared, right? And then we could also just simplify this. So we could write this as delta x whole thing squared multiplied by 1 plus fx, or f prime, xi star, and whole thing squared. Oh, the derivative squared on the inside. Yep. And then take that out. And then we could just rewrite this as delta x times the square root of 1 plus the derivative of fxi star whole thing squared. And then there we go. So we have a formula for pi minus 1 times pi to pi. So we could just go ahead and put this back into the limit formula. So we have that, well, the limit L, or the length, is the limit as n approaches infinity of the sum from I is equal to 1 to n of pi minus 1 to pi. So this is actually equal to the limit as n approaches infinity of the square root, or of the sum from I is equal to 1 to n of the square root of 1 plus f prime xi star whole thing squared and square rooted, and delta x. So now we could actually just go ahead and see that, well, we could write this as an integral now, because here our delta x here is just going to be our dx. Our square root of 1 plus the derivative of fx I star squared is just going to be written as f prime of x whole thing squared. So we would actually just get the integral from a to b of the square root of 1 plus the derivative of f of x whole thing squared and square rooted by dx. So that is going to be the integral, or the length of a curve. So this is the arc length of a curve. Okay, so let's have a look at an example. Let's use the formula that we have obtained. So let's find the length of the parabola y is equal to x squared between x is equal to 2 and x equals to 4. Well, let's first of all find the derivative of f. Let's make that easy. So if we have f of x being the x squared, then f prime of x is going to equal to 2x. And we're going to also take the whole thing squared, whole thing derivative. So f prime of x whole thing squared is just going to be 2x and then square it. So that's going to be 4x squared. So we could just go ahead and put that into the formula. So we have the length of the integral a to b, or from 2 to 4, 2 to 4, of the square root of 1 plus 4x squared and dx. So this one we could actually solve by using a trig substitution. So we're going to say let x be equal to 2 tan theta, or half tan theta. So that means dx is just going to be half secant squared theta d theta. And so if we consider the right angle triangle again, so we see that the tan inverse, so I'm going to do the tan inverse here. So theta is going to be the tan inverse of 2x divided by 1, right? Okay, so that means the opposite is going to be the 2x. The adjacent is going to be the 1. So this is our angle theta. So that means this length here is just going to be the 1 plus 4x squared. Okay, so we could just go ahead and put that in. Or because the secant theta here is just going to be equal to the square root of 1 plus 4x squared. So we could just go ahead and save some steps because the secant ratio is going to be the hypotenuse divided by the adjacent. So I could just go ahead and put this here. And then I'm just going to go ahead and substitute that in. So we have from x is equal to 2. So let's see, when x is equal to 2, yeah. So let's see what we have later on. Okay. So we have from x is equal to 2 to x is equal to 4. So I'm not doing a change of variable just yet. So if that happens, we're going to have the secant theta and then the secant square theta d theta. And we also have to multiply by a half because we have the half over here as well, which I'll put on the outside. And so that is just going to be equal to half of the integral from x is equal to 2, x equals to 4. And that's going to be the secant cubed theta, d theta, which we have computed before. Let me find the page. We computed this earlier in one of the lessons. It was going to be given by this formula here. So it was secant x tan theta I'll continue it on the another page. So we have here half multiplied by the secant theta tan theta plus the ln of secant theta plus tan theta. And this is divided by this is divided by 2 and then plus c. So here we divide this by 2. And we're going to leave out the plus c because we're doing a definite integral, so that would not be necessary. Okay, so that's our integral. So let's go ahead and substitute everything back in. So we know that secant theta is going to be root of 1 plus 4x squared. So here we would just have the square root 1 plus 4x squared. We know that tan theta is going to be 2x. And then we have the ln of the secant, which is secant square theta. Or no, the square root of 1 plus 4x squared. Plus the tan theta, which is just going to be the 2x. And the whole thing is divided by 2. And now we could just evaluate from 2 to 4. So that would just be half. So the first part, we would just have the square root of 1 plus 4 times 4 squared. This is multiplied by 2 times 4. Plus the ln of the square root of 1 plus 4 times 4 squared. Plus 2 times 4. Yep. All this divided by 2 for the first one. And then we're going to subtract it as well from the other term, but from the lower bound. So we have 1 plus 4 times 2 squared times 2 times 2. Plus the ln of the square root of 1 plus 4 times 2 squared plus 2 times 2. And all this is divided by 2. And let's evaluate the inside. So for the first part, we're going to get, so 1 plus 64. So that's going to be root 65. And then the second part here is going to be 8. So I'm just going to put it beside this root 65. And then plus the ln of root 65 once again, plus 8. So that's for the first part, and then divided by 2. Then subtract. So because we have 1 plus 4, 16, so that's going to be root 17. 4 root 17. And we have plus ln of root 17 plus 4, and whole thing is divided by 2. And so that is just going to be the arc length of x squared from 2 to 4. So if we want to visualize this, so if this is our parabola, let's say we have x squared being like this, from 2 to 4, so say here's 2, here's 4, we want to find out what this length was supposed to be. So that's the arc length here. That's what we want to find out. And that would actually be the length here. All right. So let's try another example. Find the circumference of a circle with radius r. So once again, let's visualize this. So we have the x and y axis. But what we do with the area of a circle, we do something similar. So we're actually going to be working with the semicircle here to avoid any area cancellations. So if this is our semicircle, and then later we'll just have to multiply by 2. So this is the length that we're actually working with here. That's what we want to find from negative r to r. All right. So let's start with the equation of a semicircle or circle. So we have x squared plus y squared is equal to r squared. So that means y here is just going to be, we're taking the positive since we're working with the upper semicircle, is just going to be the r squared minus x squared here. And then if we want to find the derivative, it's just going to be y prime, which is 1 divided by root r squared 2 times root r squared minus x squared times negative 2x. And that is equal to, so the 2's will cancel, and we'll just have 1 negative x divided by root r squared minus x squared. So, and then we square the whole thing, so that's y prime, whole thing squared. That is going to equal to just x squared divided by r squared minus x squared. Okay, now we just go ahead and put that into the arc length formula. So we just have the length, which is the integral from negative r to r of the square root of 1 plus, so the y prime squared is going to be the x squared divided by r squared minus x squared. And the whole thing is dx here. So let's go ahead and simplify this. So from negative r to r, we then have over here, so we have r squared minus x squared plus x squared. All this divided by r squared minus x squared and dx here. So the x squares then will just cancel out each other. And what we then have is the integral from negative r to r of the square root of r squared divided by r squared minus x squared dx. Then this is the integral from negative r to r of r divided by the square root of r squared minus x squared multiplied by dx. So this is where we're now just going to be working using a trig substitution once again. Or we could also see that this is actually just one of the derivatives for sine inverse. Because remember that the derivative or the integral of 1 divided by 1 minus x squared, this is actually just the integral, or just going to be the sine inverse of x plus c, right? So we could actually just go ahead, put instead of 1 squared, we're going to have r squared. So this is just going to be equal to then r times the sine inverse of x divided by r from x is equal to negative r to r. So that's one way you could also visualize this. To avoid any kind of trig substitution, you could just go ahead and do that if you know the integral of it. All right, so then we would just have r. So we have the sine inverse of r divided by r minus the sine inverse of negative r divided by r. So that would just be equal to r times the sine inverse of 1 minus the sine inverse of negative 1, which then turns out to be r times pi over 2 minus negative pi over 2. So that is just going to be pi times r. But that's only for the semicircle. So therefore, we multiply by 2 to obtain the circumference of the circle. So that is 2 times the length. We would just get 2 pi r, which is the circumference. Okay. So that is how you show that you can get the circumference of a circle. So now let's have a look at the next section where we'll talk about the area of a surface of revolution. So the surface area of a solid of revolution can also be found by using Riemann sums. So let's start by considering a cone with a slant height L and a base R. So we have L. So this is our cone. So here. And we have the interior. So the slant height, which is this diagonal here, that's going to be our L. And we're going to have a radius of R. All right. So let's say we cut the cone along its slant line so that we can flatten it into a sector of a circle. So that being, if we consider this sector, and then we have an angle theta here, and the arc length here is just going to be A times 2 pi r, which is the circle here that we know of. So this is going to be the sector of a circle here. And we know that the area of the here is just going to be the total area of the circle and it's going to be the angle theta divided by 2 pi. Now the theta here is going to be the fraction of the circle. So because the area of the total area of a circle is just going to be the pi times L squared, so we still have the length L. So pi L squared, then we have the theta divided by 2 pi. This then becomes the length squared times theta divided by 2. And because theta here is just going to be the A divided by L here. So we have L squared divided by 2, which is just going to be the A and divided by L. So then we'll just get A times L divided by 2. And since the A here is just going to be the 2 pi r, multiplied by L divided by 2, the 2's will then cancel out. And so we would just get the pi r times L. All right. So how I got this A divided by L from theta? Well, the theta here, we make a note that, well, theta is just going to be, or the length A is just going to be the length multiplied by theta. So if I rearranged and solve for theta, this is just theta, which is equal to A divided by L, which is the arc length of the circle. Okay, so now we just have to determine the area of a frustum of a cone. So say that we have a cone, once again. So this is our cone, of slant height L. So we have this here. And we also have another frustum. So this is called the frustum, which is sort of like the portion of a cone. And we have this part here. Oh, let me fix that one. Okay, so that's close enough. So this is the one that we want to find out. So this is part of the cone here. So we want to find out what this area is supposed to be. This entire thing here. Well, let's break it up into two parts, two slant heights. So let's say that the length here, the slant height here, we'll call this L1. And the second slant height be this here. So that's going to be our L2. And that means we'll also have two radii. So if we consider the right angle from the center of the circle, so this part here, we're going to have a radius R1. And this part here will have a radius, call it R2. Note that both of these are right angles here. So that would be important to know. Okay, so what we want to know is what is this area over here? And this part here is called the frustum. Okay. So let's draw a right angle triangle. So we draw this sort of figure. If we were to face it maybe on the right side up. So if it's right side up, we have it like this. And we divide the cone into two, and we have two radii now. So this part here is going to be the radius 1, radius 2. And then we also have the slant height, where we have this part being L1, this part being L2. Well, let's try to relate these two triangles here. Well, here we could see that, well, the length L1 divided by R1, and the other part, which is just going to be the L1 plus L2 divided by the radius 2. This is because they're similar triangles. So these are actually similar triangles. So we could actually, they'll actually have the same kind of ratio between them. So let's rearrange this, and so that we can solve for our R1L2. So that's what we want. So we have R2L1. This is equal to R1L1 plus R1L2. So we want to solve for R1 or R1L2. So let's bring this term to the other side. So we have R1L2. So this is equal to R2. So I'm going to common factor out the L1. So we have R1L2, which is equal to R2 minus R1 times L1. Okay. So the area here must not include the top and the bottom. So note, we say that the area not including the top and the bottom. Okay. So let's first see that, well, if we take the area of the larger cone, which is going to be this entire part, and we subtract it from the area of the smaller cone. So let's start with that. So the area, which is equal to the area of larger cone, minus the area of the smaller cone. Okay, so now we could actually say that, well, the area of the large cone is just going to be the pi times R2 squared, so pi, this circle, and we also have to add the slant height, so that's going to be L1 plus L2. So what we have is pi R2 squared, or pi R2, so no squared here, and we multiply that by L1 plus L2. Okay, so because it's a area of a cone, there's no squared on the radius. This should be radius 2. And then we subtract it from pi R1 L1. Right? So that's going to be this here. We only want the area of the frustum here. That's what we want. Okay, so let's go ahead and expand this. So we have pi R2 L1 and plus pi R2 L2 minus pi R1 L. Well, let's go ahead and common factor some stuff. So we see that, well, L1 we could actually common factor. So we have pi L1 multiplied by R2 minus R1. And then plus pi R2 L2. However, see this part, L1 multiplied by R2 minus R1 is exactly R1 times L2. So let's go ahead and take this formula, this is what we need, and put it into this part here. That's what we're going to change here. So now that actually just becomes pi times R1 L2 minus or plus pi r2 L2. And if we just common factor things out, we get pi. So we have R1, L2. So L2 is common. And then we just add up the radius. If I did that right. Okay, so here. Yep. And so if we call the radius here, total radius, being the, so we common factor that out. So the radius here, R, is going to be the R1 plus R2 divided by 2. So that is just going to be the 2R, which is just going to be R1 plus R2. So that we could just get the area, which is just going to be 2 pi R times L2. Or if you want, that's the area of the frustum here. All right. So we can use the surface areas of the frustums to approximate the area of a solid of revolution in the same manner we have defined areas and volumes. So once again, let's say we have a solid that looks something like this. It's being rotated along the x-axis. So say we have something that looks like this. So we had the solid, and then we break it up into many subintervals here from A to B. Okay, so if we magnify this, so magnify, and we turn each section of the cone into a frustum. So that's what we want here. So we have, if we cut this into pieces, we see that if we take this point, this point, this point, as well as this point, and this point, now we could just connect the lines here. Make sure that they're connecting each other in a straight line. Well, what about this part here? That's going to be our frustum here. Well, because the area of the frustum we know is 2 pi r times L. Well, now we could just go ahead and put this as the sum, which is we'll call the area, which is the limit as n approaches infinity. So say we have Ri, Li instead. Okay, so then we would just have the sum from I is equal to 1 to n of the area, which is 2 pi Ri Li. Well, let's have a look at a piece here. So if this is our frustum, I'll do a better one. So that's our frustum here. Now we have the length here, which is Li, and the radius, each radius here is going to be Ri. So there's going to be a lot of radii in here. So that means each Ri star is just going to be the function fxi. So similar how we define the volume. And the length here, each length is just going to be the arc length, which is something that we had talked about earlier. So that's just going to be 1 plus f prime xi star whole thing squared times delta x. So let's go ahead and put that in. Well, it turns out that the area, the surface area of a solid can just be given by the integral from a to b of the function fx times the square root of 1 plus f prime x, whole thing squared, and whole thing square rooted dx. So that is going to be the surface area. So let's go ahead and find the surface area of radius r. So once again, we know that y prime is equal to minus x divided by the root of r squared minus x squared. We know that y is equal to the root of r squared minus x squared. And we also know that y prime whole thing squared is equal to x squared divided by r squared minus x squared. So those are the three quantities we need to know. Oh, as well, we're missing another quantity. We need to make sure we have the 2 pi out here as well, because we have this constant here, so it has to go here. Okay, so let's go ahead and put that in. So we have that the area is given by 2 pi from negative r to r of the function, which is given by r squared minus x squared. And we multiply that by the square root of 1 plus x squared divided by r squared minus x squared dx. Well, we found the second part, which was just going to be, so 2 pi times the integral of r to r, the root of r squared minus x squared. We found that to be just the r divided by the root r squared minus x squared, whole thing dx. Or, yeah. And then we have 2 pi. So the root here will just cancel out. And we just get 2 pi, the integral from negative r to r of r dx. So that is just going to be equal to 2 pi times r to x from negative r to r. So that's going to give us 2 pi by r times r minus r times negative r. So that's going to equal to 2r squared. And so that means the area of the sphere is just going to be given by 4 pi r squared, which is exactly the area that we know of. Okay, so let's have a look at one more example, which actually involves an improper integral, which is going to be an interesting one. Okay, so let's have a look at Gabriel's horn. So let's say we want to determine the volume and the surface area when the graph of 1 over x is rotated about the x-axis. Okay. So, and we consider the domain for x is greater than 1. All right. So that means we have a look at this as our function. And we are already familiar that this area would actually diverge. So this is a diverging area. And as well, if we consider the horn, so we're seeing that, well, if we start from here, it keeps on going, and we consider this horn, it would just keep on going forever. So that's our function 1 over x rotated about the x-axis. And that's what we want to find out next. Okay, so let's see. I'll add an extra page just in case. So we know that the length, or the volume here, is just going to be given by pi of the integral from 1 to infinity. And the radius is just going to be the function squared. So that's going to be 1 over x squared dx. So if we compute this, that's pi negative 1 over x from 1 to t, or 1 to infinity. Well, as the function approaches infinity, we could tell that's just going to equal to 0. So that's just going to equal to pi 0 minus -1. That's just going to equal to pi. So the volume is going to be the finite part. But let's have a look at the surface area. Well, the surface area then, so we'll call this A. We know that's going to equal to 2 pi times the integral from 1 to infinity of the function which is given by 1 over x times the function 1 plus the derivative, which is -1 over x squared, whole thing squared. So y prime -1 over x squared. So that means the whole thing squared is just going to be 1 divided by x to the 4th. Okay, so we have 1 divided by x to the 4th dx. This is equal to 2 pi times the integral from 1 to infinity, 1 divided by x, multiplied by x4 plus 1, divided by x to the 4 dx. Or, this is also the same as saying 2 pi, I'll move this down here, times the integral of 1 to infinity of the square root of x to the 4 plus 1 divided by x cubed dx. Well, however, this is actually a hard integral to integrate, and it's probably not wise to actually compute this. So let's go ahead and use the comparison test. Well, for x greater than 1, we know that, well, x to the 4 plus 1 is always going to be greater than x to the 4 here. And if we divide both sides by x cubed then, so that means x cubed, x4 plus 1 divided by x cubed is greater than x to the 4 divided by x cubed. So that means it's also equal to 1 over x here. Or, let's see. No, because if we take the square root on both sides first, so we have root x to the 4 plus 1. This is still going to be larger than root x to the 4. And then divide both sides. So this is also equal to x squared. And so that means if we divide by x cubed, we just have x to the 4 plus 1 divided by x cubed, which is greater than x squared divided by x cubed, which is then equal to 1 over x. However, so let's see that, well, this integral, 2x, or 2 pi, from 1 to infinity, 1 over x dx, we know that this integral diverges. So by the comparison test, then, we then conclude that 2 pi, 1 to infinity, x4 plus 1, divided by x cubed dx diverges. So what can we conclude here? Well, we found that the volume converges to pi. However, the surface area diverges. So that's the cool thing about Gabriel's horn. You'll get a finite volume, but you cannot find a finite area. So that's the point of Gabriel's horn in this case. Okay, so that is going to wrap things up for this lesson here. So our next lesson will be beginning a new chapter. So we're going to be starting a little bit on ordinary differential equations, and we'll talk about the sort of cases that you would have to consider when solving differential equations. So until then, I will see you guys in the next video. And if you have any questions, just feel free to leave them in the comments down below.